Mr. Sibanyoni, and we are continuing with our topic, and that is electrochemistry for grade 12s. It is quite a hot Wednesday. I hope you are at school, or if you're at home, you are definitely revising. And amongst those subjects, I hope that you are revising technical sciences, because the aim is to see you get level 7s. So I hope you are ready for me. We are about to start. Make sure that you have your pen ready, your paper ready, so that you can take down some notes and actually do well in this particular topic. Then we continue. Let us look at the structure of the lesson for today. So we will revert back to examination guidelines to actually see what we are required to know for this particular topic. Because now the examination guidelines really assist us to ensure that we prepare thoroughly. And even more, in this section on the examination guidelines, we are able to get the definitions that we are required to use and the definitions that are going to be marked at the end of the year. So we will revert back to that and check what we are required to know as per your examination guidelines. And then in the features of the topic, we will be learning more of electrochemistry, but for now, we are basically going to focus on calculations of the EMF of a standard galvanic cell. So we will learn how to perform those particular calculations. We will also learn about standard conditions under which galvanic cells operate. And then in our assignment, we will look at questions on galvanic cells from previous examination papers so that we are able to concretize the knowledge that we have acquired in today's lesson, as well as the lesson on Monday and Tuesday. And the main focus will be on galvanic cells. So if we are then able to answer those particular questions, then we know we are well set to actually do well for this particular topic. And then lastly, I will be giving you more tips that you can follow to prepare for this topic when you prepare for your final examination paper 2, as well as the mark allocation that is assigned to this particular topic. Just to give you a hint, this topic alone, it's plus minus 43 marks at the end of the year. And there is quite a variety of questions that we can ask you, and hence you need to ensure that you are well conscientized with this particular topic and you are able to do well, right? So we revert back to what we are required to know as per the examination guidelines. Now for this section, I am only going to focus on galvanic cells because that is also what we will be focusing on, and not necessarily electrolytic cells for today. Now, as per the examination guidelines, the following definitions are critical for you to know because we will ask you to define those. Furthermore, you need to know and understand them because they basically help us to understand better the operation of a galvanic cell as well as the operation of an electrolytic cell. So it will be very difficult for you to be able to explain the operation of a galvanic cell or the operation of an electrolytic cell if you do not know the definitions. So let us remind each other of these particular definitions. Firstly, remember that you are required to know the definition of the term oxidation. And you will remember that when we talk about oxidation, we are talking about the loss of electrons. And you can actually use this code here, LEO, L-E-O, because this one will help you to always remember what we talk about when you talk about oxidation. And LEO simply tells us the loss of electrons is called oxidation. So just know what each letter represents there on that code, which is LEO. The loss of electrons is called oxidation. And then we know we also have reduction, which is the opposite of oxidation. So the gain of electrons, that is what we refer to as reduction. So you can use the code GER, G-E-R, which tells us that the gain of electrons is called reduction. And that is very critical for you to know these particular definitions. And remember, these are processes, these are types of reactions that take place in both electrolytic cells as well as galvanic cells. Then you must know how to define the term oxidizing agent. And for the mere fact that there we have the word agent, it reminds you that now we are referring to a particular substance. And hence, when the definition begins, it says, a substance, very critical, that is a critical word, and it must be used in the correct context. It is a substance that is reduced, or another learner could say, it is a substance that gains electrons, or another learner could say it is a substance that undergoes reduction altogether. Remember, when you talk about reduction, we are talking about the gain of electrons. So when a substance is undergoing reduction, it means the substance is reduced altogether. And you will remember the tip that I also gave you. I said to you, oxidizing agent will go with reduction altogether. So you need to remember that oxidizing agent goes with reduction, and the opposite will be true.
As you know, we brought the first generation of RDNA architecture to market in 2019 with the Radio RX 5700XT.
When you talk about a reducing agent, again, we are still talking about an agent. So we are still referring to a particular substance. So it is a substance, but now it is a substance that is oxidized. Altogether, it is a substance that is oxidized. Or simply put, it is a substance that loses electrons altogether. Or it is a substance that undergoes oxidation. It is a substance that undergoes oxidation. So, very important for you to know that, like I have told you, when a substance is undergoing oxidation, it means it loses electrons altogether. In other words, it is oxidized. And you will remember what I said to you. I said reducing agent will then go with oxidation. A reducing agent will go with oxidation. So remember that altogether, my dear learners. So you can't say oxidizing agent with oxidation, or say reducing agent with reduction. That's not how it works. It is oxidizing agent with reduction. That's the correct one. Reducing agent, it goes with oxidation. Are we clear? So that's a nice tip for you to remember. And then we must also know the definition of a cathode. We won't talk about electrolysis. It won't be our focus for today. Now, when you talk about a cathode, you will remember, my dear learners, that firstly, it is an electrode. Remember, we identify electrodes as either a cathode or an anode. So a cathode is the electrode where reduction takes place altogether. And one tip that I can give you there is remember this code, red cat, a red cat. Now I have never seen one, but we have one in science. And red cat simply tells you that reduction occurs at the cathode altogether. So always remind yourselves of those things. And the anode, again, it is still an electrode altogether. And it is the electrode where oxidation takes place. And one code that you can remember is anox. Anox simply tells me that at the anode, we have oxidation. So these codes are going to help you to really remember, because we will ask you questions based on this. Then we must be able to write down the following reactions. The oxidation half reaction. Remember now, oxidation, my dear learners, it is the loss of electrons. In other words, you must be able to show me a reaction where a substance is losing electrons altogether. And then reduction half reaction. Remember, the reduction half reaction shows us a substance, a reaction where a chemical substance or a species is actually gaining electrons, because reduction is the gain of electrons. And then the overall cell reaction by combining the two half reactions. Remember, in a cell, either electrolytic cell or galvanic cell, we have two half reactions altogether. We have an oxidation half reaction where we have the loss of electrons, and we have a reduction half reaction, which is the gain of electrons. So when you look at them individual, when you just look at oxidation, it's not the entire reaction of the cell. And that is why we call it a half reaction. Even reduction, it's not the entire reaction, it's just half of the reaction. But now, when we want the overall cell reaction, it means we want the entire cell reaction. So we have to combine both half reactions, which is the oxidation half reaction as well as the reduction half reaction. And we must know the rules for assigning oxidation numbers and be able to assign oxidation numbers to various molecules, various ions, and so on. Then, for both electrolytic cells as well as galvanic cells, we must know how to define the term electrolyte. And remember, when we define the term electrolyte, I said to you, we are going to stick to one definition, which is going to be easier for us altogether. And we said we will stick with this one. We'll say an electrolyte is firstly a substance altogether that dissolves in water to give a solution that conducts electricity. So, my dear learners, you will remember that an electrolyte conducts electricity. So for you to actually have an electrolyte, you need to take a substance, it could be in a solid form, and dissolve it in water. And that will definitely give you a solution. We refer to that solution as an aqueous solution because the substance was dissolved in water. And from that, we know the ions will dissociate, they will break apart, the crystal lattice will break apart. So the ions will be free to move, and then they will be able to conduct electricity altogether. Again, my dear learners, we need to understand the processes and redox reactions that are taking place in our galvanic cells, which is also what we will be looking at when we do the questions altogether. We must still be able to describe the movement of ions in the solutions. So we must know that altogether. For example, how ions move from the salt bridge into each half cell altogether. Either the half cell which houses the anode compartment or the half cell which houses the cathode compartment. We need to know that when we have the loss of electrons, what happens to the ions? When we have the gain of electrons, what happens to the ions? So the movement of ions is very critical. And we must be able to state the direction of electron flow in the external circuit. So we need to know the direction of electron flow, and I will remind you of this one. I said to you, electrons are lost at the anode and the electrons are gained at the cathode. In other words, the electrons must be able to move from the anode to the cathode. And we know the pathway from the anode to the cathode is via the external circuit. And hence you will say electrons always flow from the anode to the cathode via the external circuit. So remember that we don't just say they flow from the anode to the cathode. We give the entire pathway, and that is from the anode to the cathode via the external circuit. And then the following point we have talked about, writing down the half reactions, which is the oxidation half reaction and the reduction half reactions that occur at the electrodes. Now, what you need to remember is this that I've shown you. Remember red cat. I said to you reduction occurs at the cathode. So at this electrode that we call the cathode, we know that is where we will have the reduction, and we must be able to write down the reduction half reaction. And then at this electrode, which we call the anode, we'll remember the code there, anox, which tells us that oxidation, or rather at the anode, we have oxidation. Furthermore, my dear learners, and remember we are revising this, we must be able to state the function of the salt bridge, the function of the salt bridge. And remember, I gave you two functions altogether. The first function that I gave you, I said a salt bridge connects the two half cells to complete the circuit. It connects the two half cells to complete the circuit. And I said you need to be very careful there. Some of the mistakes that we see is learners will write the salt bridge connects the two half cells to complete the cell. We are not completing the cell. We are completing the circuit. So be wary of that. And we will ask you the functions of the salt bridge. Secondly, we said it maintains ionic neutrality. It maintains ionic neutrality. Or other learners could say it maintains electrical neutrality, which means instead of using the word ionic, other learners would use electrical. So the aim here of the salt bridge is to make sure that in each half cell, the solutions, the aqueous solutions, are electrically neutral altogether, which is your ionic neutrality, so that the galvanic cell can continue to operate, to work. Then we must be able again to use the cell notation altogether. And remember what I said about this cell notation. In full, we actually call it a standard cell notation. And this cell notation, or the standard cell notation, we use it to represent a galvanic cell. So sometimes we can give you a schematic diagram, which then shows you the structure of a galvanic cell. And we want you to be able to take that schematic diagram and write it in the form of a cell notation to represent that galvanic cell. Sometimes we can give you the cell notation and you must be able to interpret it and give us the schematic diagram of a galvanic cell. Sometimes, my dear learners, we can give you the oxidation half reaction, the reduction half reaction, or we can give you words, the scenario, and you must be able to take that into a cell notation or a galvanic, a schematic diagram that represents a galvanic cell. And I will remind you of this. Remember what I said to you. I said, when you talk about a standard cell notation, you will first show us what occurs at the anode. Then you will show two parallel lines to represent the salt bridge. And then you will tell us what happens at the cathode altogether. But you are not going to write it in this format. This is for the purpose of teaching. So, for example, let us look at a zinc copper galvanic cell that we dealt with, a zinc copper galvanic cell. You will remember that the zinc electrode, it underwent oxidation. It lost electrons. So the zinc atoms were changed into zinc 2+ ions. Are we together? So we had oxidation. There was the loss of electrons by a zinc atom. Which were the zinc atoms at the electrode? So Zn, which are neutral zinc atoms, they lost 2 electrons and you formed zinc 2+. And you will remember again that this zinc, which is the electrode, was in a solid form. And the zinc 2+ ions that were formed after the loss of electrons, they went into the electrolyte solution, and therefore they were aqueous. And that is why this line there, which is just one solid line, represents a line of phase change. Let me write it nicely for you. Right. It represented a line of phase change because we went from solid to aqueous. Right, still put it nicely there for you. Solid. And then that is what happened at the anode. We had oxidation. And then you put 2 parallel lines to show a salt bridge. Then you talk about what happens at the cathode. Remember, what happens at the cathode is that the copper ions, the copper 2 ions, the Cu2+ ions from the electrolyte, right? From the electrolyte, meaning that was an aqueous solution. Remember, they underwent reduction. They gained electrons and you formed a copper metal around the electrode, which was now in a solid form. That is why we also have another line of phase change, because we went from aqueous to solid altogether. So this alone gives you 3 marks. You talked about oxidation at the anode. You showed us the soul bridge. You talked about reduction at the cathode. Then this actually explains the cell notation, and we must be able to predict half cells in which oxidation will take place when the two half cells are connected. For example, my dear learners, in a galvanic cell, we know once the electrode is connected to the negative terminal of the voltmeter, it will then be the anode, because the anode is negatively charged in a galvanic cell. And if the electrode is connected to the positive terminal of the voltmeter, we will then know that it is the, excuse me, it is then the cathode. Because in a galvanic cell, the cathode is connected to the positive terminal of the voltmeter. Right? Then remember again that at the anode, we always have oxidation. In other words, the electrode that is connected to the negative terminal of the voltmeter, which is negatively charged, that electrode, then you will have oxidation. Then the cathode, which is positively charged and connected to the positive terminal of the voltmeter, it's where you will have reduction. And again, we talked about this. We must be able to write down the overall cell reaction. Basically, there, we can also call it the net cell reaction, or the net ionic reaction, or the overall ionic reaction. It just depends on the examiner. But normally, we talk about the overall cell reaction or the net cell reaction. And we must be able to use the table of standard reduction potentials to calculate the EMF of a standard galvanic cell. My dear learners, please remember this. In a galvanic cell, we will get a positive EMF altogether because the reactions are spontaneous. We talked about this yesterday. So the reactions are spontaneous, so we will have a positive EMF value. You will then remember, my dear learners, when we talk about a galvanic cell, we are talking about an electrochemical cell that converts chemical energy to electrical energy. So we will get electrical energy from a galvanic cell, and that is why we will have an EMF, and that EMF is definitely going to be positive. And that is why we actually say this galvanic cell is a spontaneous cell, meaning the reactions are spontaneous. They actually do not require any form of electrical energy to occur. And there they tell us we must use a positive value of the standard EMF, right, as an indication that the reaction is spontaneous under standard conditions. And this we will talk about as well today. What are those standard conditions under which a galvanic cell operates? And we must be able to determine the electrode potential of a copper zinc cell. Altogether, we must be able to do that. And not only this one, my dear learners, this will use as an example for today, but you must be able to then use it for any form of galvanic cell. And lastly, not lastly for the entire topic, but for what we are still focusing on, which are your galvanic cells, we must be able to write down the standard conditions under which standard electrode potentials are determined. In simple terms as well, its standard conditions under which this galvanic cell would be operating. Right. Now we get into the main details or the main content for today. Now, my dear learners, standard electrode potentials, they are very important in chemistry. They are very important to understanding redox reactions, to understanding electrochemicals reactions. Now, we know that we are required to calculate the E0 value of a half cell, the E0 value of the second half cell, but we are also required to calculate the EMF of the cell, which is the E0 value of a cell. So here, my dear learners, we say the E0 value of a half cell is an indication of the tendency of a specific substance to undergo oxidation or reduction altogether. Now, when you go to table 4B, we have a table of standard reduction potentials. Right. Now, a table of standard reduction potentials, my dear learners, it looks like this. Now, this table of standard reduction potentials, I told you that we are going to look at table 4B altogether, and it is a table of standard reduction potentials. Now, this table, my dear learners, you can see for every substance that appears there, you have an E0 value. And this E0 value gives us an idea of the tendency of these substances to either undergo oxidation or reduction. And to put it simply, you can see we call it a table of standard reduction potentials. And we don't call it a table of standard oxidation potentials. It's that of reduction potentials because the E0 values there actually tells us, and to put it simply, how much a particular substance loves to undergo reduction. So the lower the E0 value, the less likely the substance will undergo reduction. So a substance that has a lower E0 value doesn't like reduction like the substance with a higher E0 value. So to put it simple for you, the lower the E0 value, the less likely it will undergo reduction. The higher the E0 value, the more likely the substance will undergo reduction. So for example, my dear learners, when you look at lithium and you look at lithium ion gaining 1 electron to form lithium and potassium ion gaining 1 electron to form potassium, neutral potassium atom, we can see the E0 value of lithium ion to undergo reduction to gain electrons, it's negative 3.05, but that of potassium, it's negative 2.93. So that of lithium plus is less than that of K plus. In other words, the reduction potential of potassium ion is greater than the reduction potential of lithium ion. So the potassium ion loves reduction more than the lithium ion altogether. And therefore, if I had a galvanic cell where I connected a lithium half cell and a potassium half cell, then the potassium half cell would be the one that undergoes reduction. And the lithium ion the lithium will be the one that undergoes oxidation altogether. So the potassium ion would undergo reduction the lithium atoms of the electrode would undergo oxidation. So remember this. I want to put it simple for you, my dear learners, because now we know the higher the E naught value, the more likely it will undergo reduction than the other substance. So simply, if you compare two half cells, the one that appears on top for table 4b will undergo oxidation, the one at the bottom will undergo reduction. Let me give you an example. Let's say I connected a magnesium half cell with a nickel half cell. Can you see? Magnesium is on top and the nickel is at the bottom. In other words, nickel loves reduction more than magnesium. So if a galvanic cell is made up of a magnesium electrode as well as a nickel electrode and magnesium ions electrolyte and nickel ions electrolyte, then reduction will be by nickel ions and oxidation will be by magnesium. So the one that is on top of the other one will undergo oxidation, the one at the bottom will undergo reduction. So you just look at the spaces that you are comparing out together, right? Then we continue. And what I said simply applies to table 4b. It doesn't apply to table 4a. And that's why I said we are only going to deal with one table, which is table 4b. Then those electrode potentials have been measured under standard conditions altogether. They were measured under standard conditions. And we'll talk about this later because they are measured, you know, when the cell is one half cell that we are interested in, it's connected to a hydrogen half cell. But we are not talking about that for now. But my dear learners, please, we will ask you for 3 standard conditions under which a galvanic cell operates altogether. And firstly, those reduction potentials that we saw in table 4b were measured when a galvanic cell operates at a room temperature of 25 degrees Celsius, which is actually equal to 298 kelvins. Now, when we ask you, write down 2 standard conditions under which this cell operates, learners tend to write only the value and say 25 degrees Celsius or write 298 kelvins. That is wrong, my dear learners. You have to write in full altogether. The standard conditions is a cell operating at a room temperature of 25 degrees Celsius altogether. And then the electrolyte concentration. Remember the electrolyte, the solution that is in each half cell. Its concentration must be 1 mole per decimeter cube. And you can't say concentration of 1 mole per decimeter cube. We want to know that it is the concentration of the electrolyte. So you write it as it is. Electrolyte concentration of 1 mole per decimeter cubed. And remember, there we have a dot, and there it must be a -3 because that's what per means. So what we often see is that learners would write mole dot dm cubed. This is mole decimeter cubed. So it's incorrect altogether because there it must be a negative. Others would go as far as writing mole dm -3. It's wrong because now this looks like one thing. We must have a dot. So this is still incorrect. Other learners would write okay, this is more or less, yes, what we often observe when we mark you. So please take care of that. Now, these two conditions, these two are always applicable for any galvanic cell, any galvanic cell. So if we ask you, write down two standard conditions under which this cell operates, please, my dear learners, I'm giving you a tip. Always start with these first two because they are applicable to the galvanic cell. If we ask you for three standard conditions under which a particular galvanic cell is operating, then you must know that we are dealing with one half cell, either being a gaseous half cell or both of them being gaseous half cells. And there you will say a pressure of 101.3 kilopascals. And that's exactly how you write it and how you write your units. 101.3 kilopascals. Or another learner could have said it's 101,300 pascals. Altogether, this is when you say it in pascals. But this is only applicable when you are dealing with either half cell, or either one of the half cells being gaseous or both half cells being gaseous. Like let's say you have a hydrogen half cell connected to a copper half cell. Then because we have a hydrogen half cell, we are dealing with hydrogen gas there, then this one will be applicable. But if I was dealing with a zinc copper galvanic cell, then this one does not apply because there is no gas here in both of the half cells altogether. So you will only mention this one if we are talking about gases altogether. Then we talked about these ones, what they actually represent. I've talked about that. Now, table 4b, my dear learners, I've also indicated to you what it means. Remember, I said to you, the one that is on top, right? If you compare two, the one that is on top will undergo oxidation altogether, right? So at the top, we have the substance that will undergo oxidation. In other words, it's a strong reducing agent. Remember, oxidation goes with reducing agent. So if a substance undergoes oxidation over the other one, it means it is a stronger reducing agent because oxidation goes with reducing agent. And then at the bottom, remember I said when you compare two, the substance that will be at the bottom will undergo reduction altogether. So if it undergoes reduction, it means it's not a strong reducing agent. It's actually a weak reducing agent. And to make it simple for you, the one that is at the bottom, my dear learners, there, it will be the strongest oxidizing agent. Always remember it like that altogether, because reduction, my dear learners, we associate it with oxidizing agent. So the substance that gains electrons is the oxidizing agent, which undergoes reduction. So at the top, remember, oxidation, strongest reducing agent. At the bottom, reduction, strongest oxidizing agent altogether. Now, when you go to table 4b, each half reaction can either be used as reduction or oxidation altogether. So if we ask you to write down the oxidation half reaction or the reduction half reaction, my dear learners, you will remember very well that you have to use single arrows altogether. And we talked about this yesterday because then you would know that the substance on top is undergoing oxidation, so we use one arrow. The substance at the bottom is undergoing reduction, so we use one arrow altogether. So remember that. So We now want to learn how to calculate the EMF of a cell. Now, when you go to table 4B, let's say we have a zinc copper galvanic cell, the one that we talked about yesterday. We saw this one, where one of the reactions, or rather, from table 4B, we have zinc 2 plus 2 electrons, double arrows, Zn. Then we had copper 2 plus 2 electrons, double arrows, forms copper. And we noted that zinc is on top. In other words, we will have oxidation altogether. So the Zn atoms, we know they undergo oxidation because Zn is on top. And then the copper 2 plus, we know they undergo reduction because they gain electrons. So we've already written the oxidation half reaction before and the reduction half reaction and the net cell reaction. That's not what we are looking at for now. Now, this is what I want you to see, right? Look at table 4B. Can you see that there we have this one? Zinc 2 plus 2 electrons forms Zn. And then we have copper 2 plus 2 electrons and it forms copper. So Zn, this one, it's on top with the zinc. Here with the copper 2 plus, it's at the bottom. It means there we had oxidation, there we had reduction, because I said the ones on top, they love oxidation. They are stronger reducing agents. The one at the bottom, they undergo reduction because they are stronger oxidizing agents. So we are comparing those two, right? Then we go, just note the reduction potential for zinc, it's negative 0.76, and for copper 2 plus, it's positive 0.34, right? So we go back. There we go. So copper 2 plus has a stronger tendency to undergo reduction. We talked about that than zinc 2 ions, and zinc has a stronger tendency to undergo oxidation than copper, than Cu altogether, right? Therefore, if we want to calculate the EMF of the cell, we'll say E naught cell is equal to E naught reduction minus E naught oxidation. My dear learners, the formula is written like this in the formula sheet, and you will write it exactly like this. We don't want to see someone write E naught red minus E naught ox. No, you take it as it is from the formula altogether. Some will write E naught C is equal to E naught R minus E naught O. No, no ways. We agree, my dear learners. You take the formula as it is. So we know, okay, according to this formula, the substance that is undergoing reduction is the Cu2 plus altogether. So under reduction, we'll write positive 0.34. Right? Normally we'd give 1 mark there, minus, which comes from the formula. For oxidation, we know zinc, Zn, this substance underwent oxidation, and the reduction potential was negative 0.76. That's another mark, and then the value is 1,10 volts. And we know this value is positive. And because of this positive value, we then know that, yes, chemical energy was converted to electrical energy. And we know again that this reaction is spontaneous because the EMF of the cell is positive. Good. So this, my dear learners, it's actually what I've been saying to you. It's not much there. And remember, for now, I used my formula in the form of E naught cell is equal to E naught reduction minus E naught oxidation. But when you go to your formula sheet, you will see that you can use the different versions. One of the versions is to say E naught cell is equal to E naught oxidizing agent minus E naught reducing agent. And it makes sense. You know that reduction is underwent by an oxidizing agent. And you know oxidation is underwent by a reducing agent altogether. That is why when we define an oxidizing agent, we say it is a substance that undergoes reduction. When we define a reducing agent, we say it's a substance that undergoes oxidation. So it means the same thing. Again, we know reduction occurs at the cathode. We know oxidation occurs at the anode. So any of these, they mean the same thing. It's just we write the different alternatives. And even here, my learners, you will write cathode in full, cell in full, anode in full. No abbreviations. Cell in full, oxidizing agent in full, and reducing agent in full. Altogether. Then let us do a question. A question says, calculate the cell potential. Number one, my dear learners, you know there, when you talk about the cell potential, we are talking about the EMF. So we're calculating the cell potential of a galvanic cell consisting of lead and magnesium electrodes functioning at standard conditions. You definitely know that, oh, now we are dealing with lead and we are also dealing with magnesium electrodes. So again, they are functioning at standard conditions. In other words, I can actually go to my table 4B and use those reduction potentials. Why can I do that? Because those reduction potentials were measured under standard conditions altogether. Right, and we also want the EMF under standard conditions, which we call then the cell potential. So it will be E naught cell, it's E naught reduction minus E naught oxidation minus E naught oxidation. Then this is what we want. We took the formula as it is from the formula sheet. You see there, E naught cell is E naught reduction minus E naught oxidation. So we must then go check with the lead electrodes. Remember, lead is Pb and magnesium is Mg. So we are going to look at them and we'll identify where we have oxidation and where we have reduction. So we go to table 4B again. Good. There we go. Let's find magnesium and lead. There we go. I see the magnesium there. And then I want lead. If I go down, there's the lead. So by just checking there, can you see that the magnesium is on top? So we agreed that according to table 4B, if magnesium is on top, then it undergoes oxidation. The lead is at the bottom, so it will undergo reduction. So let us just check the values there. For magnesium, it's negative 2.36, and for lead, it's negative 0.13. Then we go back. We say, okay, the lead was at the bottom, so it will undergo reduction because it's the strongest oxidizing agent, and its value was negative 0.13 minus E naught oxidation. And we saw that the magnesium electrode is the one that will undergo oxidation because it was on top. It was a stronger reducing agent, a stronger reducing agent. And if I remember well, we saw that the value is negative 2,36. And then we go to our calculator and we say, okay, negative 0.13, right? We are simplifying now. Minus into negative 2.36. So the learners will know negative times negative gives me positive. So it will be negative 0.13 plus 2,36. And then if you do your mathematics there, you will see that it will give you positive 2,23 volts altogether. And this is how we would mark it. 1 mark there, 1 mark for the substitution of E naught reduction, 1 mark for the substitution of E naught oxidation, and the final mark for a positive EMF because we are dealing with a galvanic cell. My dear learners, we are definitely going to ask you to perform this calculation altogether because in paper 2 we don't have much calculation. So where we get an opportunity to give you questions, then we are definitely going to do that. Lastly, I want to give you tips in terms of how to prepare the section that we have talked about. Stick to only one table. Table 4A or table 4B. For the purpose of our online lessons, I am sticking to table 4B, and that is the table that is commonly used. If you are used to table 4A at your school, it is okay. Stick to table 4A altogether. Just make sure that you understand it thoroughly. Table 4B, be able to remember how to interpret it altogether. It's your table of standard reduction potentials. The lower the reduction potential, the less likely the substance will undergo reduction. The higher the reduction potential, the more likely the substance will undergo reduction. So that is how you check. And as a recipe for you, remember, when you are comparing two electrodes, for example, zinc and copper, you will see that zinc is on top and it has a lower reduction potential. So it will undergo oxidation because it is a stronger reducing agent. And the copper electrode is at the bottom. So the copper ions are more likely to undergo reduction because they have a higher reduction potential altogether. And then you will be able to write down your oxidation half reactions as well as your reduction half reactions and your net cell reaction. And from that, you can also calculate the potential difference of the cell, which we can sometimes call the cell potential. Sometimes we can call it the cell potential difference, or we can simply call it the EMF of the cell. And you will have to use those formulas as I have given you, because that's exactly how you will get them in your formula sheet. And then you will use the values from table 4B to calculate whatever we are asking you, which would then be the EMF of the cell. Right. And remember, this topic is plus minus 43 marks. So we definitely want you to do well altogether. Right. So remember to send me more questions to stemdigitalschool@africateengeeks.co.za, and I can help you with any question that you have on this particular topic and also in preparation of our question and answer session on Saturday. Thank you so much for tuning in. I will see you tomorrow, same time, same place. I hope you enjoyed the lesson as much as I did, and thank you for tuning in. Goodbye.